Hi and welcome to another episode of Ordinary Differential Equation. We are talking about modeling with first order equation, and today we are going to take a look at population forecasting. Let's go and meet the cast of characters in this story. So we have a population story to say. Population forecasting simply refers to trying to find out how many of a certain members of population are going to be out there at some time in the future. So as usual, our basic variable is time. It might be measured in years, or it could be measured in days or weeks, or whatever unit might be in the case. You pay attention to that in the problem that you solve. There is always some initial population that is specified, and for that population a growth rate is typically given, and as an additional twist to the problem, there could be some sort of a harvesting or a predator perhaps consuming this population. So we are going to have a harvesting rate is shown by something like K. What we are aiming for is finding the population at some time t and some analysis that refers to this population. Remember that we have this basic problem solved before, and we are going to make frequent use of it. If y prime is ay plus b and b being constant numbers and the initial value of y is given for us, then y for all times in the future can be specified by this formula. So we go ahead and write our model. How are we expecting for this population to grow? As usual, we have two sources that are going to influence the growth of the population. One is the population is going to grow by itself, and that is proportional to how many members of the population we have and what the growth rate is. So first, simply the change in the population is due to these two factors, R and P itself. If we have harvesting, then we are going to lose members of this population to that harvesting. In case if we had a restocking of some sort or some additional members coming into the society, then we'll be adding a K. So in this case, we are taking a look at the harvesting problem and see how that is going to influence our problem. P, as usual, at time 0 is given to us, and that is P sub 0. Making use of this formula that we have developed before, we can immediately see what the population at time t is going to be. So minus b over a, who is playing the role of a and b. Of course, this is our a, and this one is our b. And population, therefore, minus b over a is going to be k over r, and then initial population, whatever that is, plus b over a. Plus b over a is going to become minus k over r, and then exponential of rt. So that was rather quick. Now, what could we be interested in? The fact that this is negative at some values of our parameters makes the problem somewhat interesting. Let's go ahead and write an example and see how this plays out. So we are going to consider a population of certain, say, field mice. Consider a population of field mice. Well, who is harvesting field mice? In this problem in your textbook, they are interacting with owls. The owls are consuming the field mice at now here's idealization, at a constant rate, as if they had a ration of being allowed to eat only so many mice per day or something. Consider a population of field mice interacting with their predators. Let's consider the owls as their predators in this problem. So in situations like this, the population equation that we write typically is very idealized. It's just for the sake of building a story around the differential equation. True differential equations are substantially more complicated than this, but it gives us an idea of a generalized trend. So these field mice are interacting with owls, and we want to know, describe conditions under which the mice become extinct. So sometimes you introduce a predatory animal to a reserve, and then you lose the inhabitants that you had in that location. So this is going to give us some simple approach to that issue. When would extinction going to happen? And we want to find out, for example, the time to extinction. So we want to analyze the problem in that regard. So we look at this and we say, okay, if P0 is larger than K over R, then the population is going to be always positive. K over R is positive. If this is positive, exponential of RT is always positive. The population is going to keep growing and it's not going to become extinct. However, if it so happens that K over R is more than P0, remember K was the number of mice being eaten by the owls. If owls have good appetite and they eat a lot of mice, if it so happens that K over R is more than P0, this factor is going to become negative. And this factor becoming negative eventually makes this expression to be 0, meaning the population has been reduced to 0. At that point, the creature has become extinct. Mathematically, this goes into negative numbers, but of course, negative population does not mean much. So what we are going to do, say if you have P0 minus K over R positive, if this is positive, the population is going to grow and approach large numbers. So we say population grows without bounds. In fact, they are going to grow exponentially. We need not worry about them. If P0 minus K over R is 0, then population is going to will be constant. So if this factor is 0, population for all times is going to be just K over R, and that is its original value. In that rather headline making situation will be if P0 minus K over R were negative. If it is negative, at some time in the future this is going to become 0. So we go set it equal to 0, K over R plus P0 minus K over R times exponential of RT is equal to 0. So what could be expected out of this? We want to find time to extinction. Find well, we have to rearrange this thing and calculate the t out of this. It's going to be simple, so I write P0 minus K over R exponential of RT, and I take my number to the other side. Now I divide, so our exponential of RT is going to be minus K over R over P0 minus K over R. To make this formula look nicer, I'll multiply by minus both on the numerator and denominator. If you want to perhaps make the formula look simpler, we can multiply numerator and denominator with R over K. So one way of simplifying, multiply by R over K. So that's a reciprocal of this number. What happens is that this becomes 1, this also becomes 1, and then we have R P0 over K. So we have collected all of our factors in one number as opposed to having them all over the place. So next I take the logarithm from both sides. So RT becomes a logarithm of 1 over 1 minus RP0 over K. You remember from pre-calculus that logarithm of a ratio is negative of logarithm of numerator minus logarithm of denominator, which in this case logarithm of numerator is 0. So this becomes minus logarithm of 1 minus RP0 over K. So time to extinction, let's write this as TE. E for extinction is minus 1, I have to divide by R, logarithm of 1 minus RP0 over K. So of course this is a number less than 1, and logarithm of that will be negative. That's going to cancel this negative, and overall we are going to get a positive quantity. So some problems you will come across a situation like this, and this was a simple application of ordinary differential equation of first order. Now later on we are going to take a look at the population problems in a much more sophisticated way. This was a rather simplistic model, but it just shows to us what we can do with a simple differential equation. So what we found here is the extinction happens if this is less than 1, or if you cross multiply it, it becomes R P0 over K is less than 1. So let's just emphasize this is good so long as, of course, R P0 over K is less than 1. Again, meaning the consumption of field mice by the owls is so high that fraction has become small, that eventually make the mice go extinct. Okay, next time we are going to take a look at another example. Until then, good luck and God bless.